this section is related rates. This is not a technique, but it's more of a principle that can be used to solve problems where you want to find or calculate an unknown rate of change in terms of other rates of change that are given to you. So this is only possible, it can only work when, well, there's a relation between the two quantities. And usually that happens because it's a geometric constraint. Well, to explain this better, I think we can use an example, perhaps the most classical example, so the canonical one, which is the sliding ladder problem. So the setting is the following. So you're given a ladder that is leaning against a wall, so something like this, and as it slides down, slides away from the wall, you see that the height is decreasing because there's a relation between the y coordinate and the x coordinate, because the length of the ladder has to remain the same for all time. So what we see here, what we'll see in this problem, is that the bottom, even though we're going to prescribe that the bottom will travel the same distance over each time interval, but the top will travel farther during subsequent time intervals. So the top in the end will be speeding up, while the bottom will move at a constant speed, at a constant rate. So what is the problem? The problem is the following. We are giving a 5-meter ladder that is leaning against a wall, and the bottom part of the ladder is 1.5 meters away from the wall at the beginning, so at time t equals 0. And slides away from the wall at a constant rate, at a rate of 0.8 meters per second. And we're asked to find the velocity of the top of the ladder at time t equals 1. So here we're given that the rate, as I said, of one of the variables here is 0.8 meters per second. That is the distance from the origin of the bottom part. And we have the initial position of the bottom part, which is 1.5 meters. And the geometric constraint that we're going to use here, there's always something like this. There's always a geometric constraint. So it's a way of using implicit differentiation here to relate two quantities and their derivatives. And so if you remember that from the previous section, what we usually have is a relation between x and y, or x and h, which is what we're going to call here. And the constraint here is that the ladder is of 5 meters. Okay, we're going to use that. So the solution goes like this. So first step, we need to choose our variables. So choose variables. And so x here is going to be a function of t, x of t, which is going to represent the distance from the bottom of the ladder to the wall, and h here is going to be again a function of time, which is going to be the height of the ladder's top. And what do we know? We know what? We know that x prime of t is constant and it's equal to 0.8 meters per second. And at time equals 0, x of 0 is 1.5 meters. Now we have the geometric constraint. So here we have the wall, and this here represents the height, and this is x of t. And the hypotenuse here is the ladder, so it's the length of it is 5 meters. Right, so we have thanks to Pythagoras, the constraint so Pythagoras implies that h squared of t plus x squared of t is equal to 5 squared meters squared. You see, so we need that. Remember, we need two things: the geometric constraint, which relates x and h, and we have information about x. We know that x prime is 0.8 meters per second, and x at time 0 is 1.5 meters. And so from that information, we can find out the velocity of h at a time equals 1 for this particular problem. Okay, so now we have the relation here. How do we relate the derivatives? We can differentiate. We always differentiate the constraint. Okay? And this will give us that 2h of t times h prime of t. Remember, we're differentiating with respect to t. This 2x of t, x prime of t is going to be equal to 0 because, well, the derivative of 25 is 0, which is 5 squared. It's constant. Here we can forget about the 2's. And this tells us that h prime of t is equal to minus x of t times x prime of t, all that divided by h of t. So we need to find h prime at time h prime when h is time equals 1. H prime is, so this was correct actually. So we are asked to find h prime at time equals 1. And so how can we do that? Well, we have a relation here. H prime is given here in terms of x, x prime, and h. So we need to know h at 1 and x at 1. So we know already the x prime is constant. It's constant and it's equal to 0.8 meters per second. So we need to find x at 1 and h at 1, and then we'll be able to find what h prime 1 is. So what is x at 1? Well, we use the fact that the speed is, the velocity of x is constant, and so 0.8 meters per second is equal to delta x divided by delta t, or x at 1 minus x at 0, but it won't minus 1 minus 0. And here we already know that, well, we don't know what x1 is. This is what we want to find out. And we know that at time equals 0, x is equal to 1.5 meters. And this is divided by 1 second. So we multiply by seconds here, we obtain that 0.8 is 1.5 meters is equal to x at 1. So in the end we get that 2.3 meters is equal to x of 1. Now we need to find what is the value of h of 1. And for that we come back to Pythagoras here. This is valid for all time. In particular, we can plug in the value t equals 1. And again, back to Pythagoras, we know that h squared at 1 is x squared at 1 is equal to 5 squared meters, so 25 meters squared. This implies then that h squared at 1 is equal to 25 meters squared minus x squared at 1. But we know that this is equal to 25 minus 2.3, all that meters squared. 2.3 squared, I'm sorry. Okay, so taking the square root, we know that the height cannot be negative. We know that h at 1 then must be equal to the square root of 25 minus 2.3 squared meters. If you use your calculator, you'll see that this is approximately equal to 4.44 meters. Okay, so we know x at 1, which is 2.3 meters, h at 1, 4.44 meters, and x prime is already given to us to be equal to 0.8 meters per second. So that means that h prime at 1, in sum, h prime at 1 is minus 2.3 meters times 0.8 meters per second, all that divided by h at 1, which is well, okay, it's not equal to this, but you get the idea. So if you can compute this, I mean you will use this value here as the actual value, just for illustrating the method. So in the end, this gives us something that is close to, or approximately equal to, minus 0.41 meters per second. So at time 1, h prime is approximately equal to minus 0.41 meters per second, and that is what we were asked to compute. Okay, and it's negative because the top of the ladder is moving away towards the origin, so it's moving in the negative direction. And so this is the first application. This is the first problem. I'll see you in the next video.